Hey Trade Kids, I'm homesick today, so I am sending this into you on Google Classroom. We're going to go through probably a good chunk of section 5.2. We might not get done with it, but starting into exponential functions. So we have, we've talked about exponential functions in algebra and stuff before. The graph of those look like just kind of a curve. It will intersect at the point 0, 1. So its y-intercept will always be 1 until we start to move him around. And he'll also have a horizontal asymptote at y equals 0. That's where his ha will be, okay? And this is for an exponential growth. An exponential decay will look like this, still intersecting at 0, 1. Still having a horizontal asymptote, except he'll be going downhill, okay? Examples of growth versus decay for in a formula, like an exponential growth would be like y equals 2 to the x power. This is something that's doubling over time, which a lot of times you see in like science, where you'll have like bacteria in a petri dish or something. You might have 2 to start with, and then 2 becomes 4, and 4 becomes 8, and 8 becomes 16, and it's doubling over time, and it's increasing its population and going up and up and up, okay? An exponential decay will be like y equals 1/2 to the x power, okay? And that's splitting everything in half. So maybe like things are dividing, or a population is decreasing. It's halving each time. So maybe you're starting with 64, and then you're going to 32, and then you're going to 16, and then you're going to 8, and then going to 4, etc. As time passes, okay? In a formula, you can tell whether it's a growth or decay based upon the number that is here, okay? If it is a number that's greater than 1, it's going to be a growth. If it is a number that is less than 1, but greater than 0, it's going to be a decay function. A lot of people say if it's a fraction, it's a decay. Well, that's not necessarily true, because 3 over 2 is a fraction, but 3 over 2 equals 1.5, which is actually a growth. So that's kind of how that works. So the two graphs of each of those, one's a growth, one's a decay for exponential functions. The first couple examples that we're going to do is translating these things, okay? So we have the graph of 2 to the x power. So these are things that are doubling each time. And we need to look at what is happening when we, like, let's say, add the 3 up in the exponent with the x, okay? Now, there's a difference between 2 to the power of x plus 3 and 2 to the x power plus 3, okay? So here's the difference between those two. This one is going to be left and right, shifting the graph left or right, and this one's going to be up and down. Okay, more specifically, this one's going to be up 3, and this one is going to be going to the left 3. So the plus actually, this is kind of like, this is in parentheses, the plus there actually means the opposite of what you think it is. Here, the plus means up. So there's no difference there, but this is kind of like when it's in parentheses and you use the opposite symbol, okay? So here we're going to the left 3 units with the graph of 2 to the x power, okay? So 2 to the x power, I said it intersects at 0, 1. We're going to shift that to the left 3 units, and he's actually going to intersect there at 0, 1. So he's going to do something like that instead, okay? Part B, you have 2 things that are happening. You have the -3, and then you have the -4. Okay, so I was going to order, like, if I were to plug a number in for x, we would apply the -3 first. So the -3 is the first thing that we would do. And then we would subtract the 4. Is the second thing that we would do. So the -3, since he's up in the exponent, it's kind of like in parentheses, that is going to the right 3 units now. And the -4 is going down 4 units. So this is kind of like stuff that we've done before. It just looks a little different when we're doing exponential functions. Okay, let's go down to horizontal stretches and compressions. When we have stuff in the exponent, that's going to be when it's a horizontal function versus, like, let's say this was y equals 0.2 times 3 to the x power. This is going to be a vertical stretch or vertical compression. This is going to be a horizontal stretch or compression. Okay, so whether it's up in the exponent versus down in front of the function, that's the difference between the two. Okay, so this first one, 0.2 to the x power. We have 3, and we have 0.2 to the x power is the exponent. I don't like to write them in terms of decimals. I always like to put them as fractions. So 0.2 is 1/5. Okay, now the rule for horizontal stretches and compressions is that this number right here, we always have to flip it. Okay, so it will be a horizontal stretch actually by a factor of 5 because I flip the 1/5 and it becomes a 5. Okay, versus if it was 0.2, if it was like 1/5 here times 3 to the x power, this would actually be a vertical compression by 1/5. You do not flip it if it's a vertical one, but if it's horizontal, it's up in that exponent, then you do flip it. Okay, if I'm going too fast, please pause this video so you can get all these notes written down. 0.8 to the x power, that is 4/5 times x. And so we're still up in the exponent. We're still doing a horizontal stretch or compression, but my factor is going to be flipped of those two. It's going to be 5/4. And then we have to decide, okay, is that a stretch or is it a compression? Well, since 5/4 is a number larger than 1, it's going to be a stretch. So horizontal stretch by a factor of 5/4. So we're making it a little bit larger than what it was before. All right, now we have negatives that are involved. Okay, and the rule for negatives is if it is 3 to the negative x power versus negative 3 to the x power, this is over the y-axis, and this one's over the x-axis. Okay, so those are those rules. If you have a negative in the exponent, it's over y. If you have a negative down in front, it's an x. It's over x. So this guy is just reflecting over the y-axis. Okay, now you might be wondering, like, there's a 3 there that we haven't been dealing anything with. Like, we haven't done anything with the 3. We haven't done anything with the 3. Anything with the 3. Well, our parent function was 3 to the x power. So the 3 is not doing anything. The 3 was already there. We're just doing, looking at what additionally is going on. So 3 to the x power, if you're wondering why we haven't done anything with that 3, that is why. Okay, now here for this last one, we have two things going on. We have the negative and we have the 0.4 that are happening. So there's two things that are happening. And you can do these. Technically, they're being applied at the same time. The negative and the 0.4 are being applied at the same time. So you can do these in any order. If I were to plug a number in for x, it's like, would you apply the negative or would you take it times 0.4? They're kind of both happening at the same time. So it doesn't really matter. Let's go ahead and do the 0.4 first and then do the negative. We know that the negative in the exponent is going over the y-axis, but the 0.4 is 2/5. Okay, and since it's up in the exponent, it's going to be either a horizontal stretch or compression. But let's go ahead and flip it and figure out what the factor is. So it's going to be by a factor of 5/2 rather than 2/5, and that's going to be a horizontal stretch by a factor of 5/2. So that's that one has two of them. So both of those are the answer for that. Okay, how we are shifting it. Okay, they want us to go ahead and graph each of the functions. So let's say, okay, let's just do this. Let's say this is 3 to the x power. Okay, a horizontal stretch by a factor of 5 horizontally means we're making it fatter. So he's still going to come along, but he's going to be a little wider than normal, right? So that's kind of what that first one is going to look like. Okay, this one is a horizontal stretch by a factor of 5/4. So we're still stretching it by a factor of 5/4 instead this time. So he's going to be stretched, but 5/4 is only 1.25, so it's not going to be as much of a stretch, but just that. Okay, so it's not as much as the first one, but it's still stretching it a little bit. Okay, let's go over and do a new graph for these two. Let me move this down a little ways. Okay, so if this is my original function, again, he's intersecting at 1 right here. He's going over the y-axis, so he's going to flip this direction and be going downhill. So really, this negative flips it from being an exponential growth function here to an exponential decay function here. So that is something that kind of happens as well. And then a horizontal stretch by a factor of 2 and flipping over the x-axis, we're going to be stretching him out horizontally, so making him fatter, but then we're also flipping him, so he's going to look like this. Something like that. He's going to be a little wider than normal, okay? So that's kind of, this is this piece right here. A little wider than normal, but flipping him over the y-axis as well. Okay, and again, that's just kind of a rough sketch. You could put those in your graphing calculator and probably get a better approximation or a better look at what the graph of those look like. But that's kind of how those take place. Okay, let's go to the next one. We've got a couple more things, and now they are going to put a lot of numbers in here. Okay, so we've got to identify a bunch of different things that are happening. Okay, so our original function is, I guess we don't have too much going on. Our original function is 3 to the exponent of negative 0.4x. So this is our parent, okay, which is parent, which is kind of different because usually they'll only go like 3 to the x power or something. So 3 to the negative 0.4x is our parent function, which is really this guy here. So I guess we don't have a bunch of stuff going on. All we have that's changing is this 4. And that 4, since it's on the outside, I kind of gave you a little hint over here. If it's a number on the outside, it's going to be a vertical stretch or a vertical compression. Okay, so on the outside there, this is going to be a vertical stretch by 4. We don't flip it like we do with the horizontal ones, like we do with the ones up in the exponent. We just say vertical stretch by 4, okay? Because our parent function was already starting with this stuff, okay? Let's go over here, and this one, we're already starting with that. That's our parent function, so then we just have to decide what the negative 2 is doing. And actually, there are two things that are happening. The 2 is doing something, but also the negative is doing something. And they're kind of being applied at the same time, so it doesn't matter which one you do first, okay? The negative, since it's on the outside, is over the x-axis. That's one of the rules, okay? So this guy is going over x. And then the 2 is vertically stretching by a factor of 2, okay? This graph kind of makes it look like it's compressed a little bit because normally an exponential function I would do like this maybe a little bit. I don't know. Oh, no, this is the original. Yeah, this is the original function of what he looks like. Okay, so let's, on that graph, let's do vertical stretch by 4. So vertically stretching him by 4 is going to make him taller and skinnier. So he's just going to look like this a little bit. I don't know, that was really bad. For that first graph, he's going to look something like that, okay? For the second one, we're taking, again, this original guy, and we're flipping him down over the x-axis and vertically stretching him by 2. So we're going to make him taller and skinnier, but he's going to go this direction instead. So he's a little bit taller than what this one is, but we flipped him down instead. So that's what this guy is right here, okay? Again, those are just rough estimations of what each one of those looks like. But that kind of gives you an idea on what each one of those graphs is doing. So when we look at exponential functions down here, we can kind of see what each one of these numbers is telling you, okay? All right, so that is all the graphing stuff, and now we get to story problem stuff, okay? We'll do a couple of these story problems, maybe do these two, and then we will stop, and I'll give you time to start on your homework assignment. So exponential growth, exponential decay. We're not actually solving any functions yet because we don't know how to solve exponential functions yet. We have to use like logarithms and stuff. But we're just going to be, for these next two problems, just plugging things into our calculator. So if you invest $500 in a stock that is increasing in a value at 3% per year, this is what the function will look like. Okay, so let's break that down. 5,000 is going to be your starting value. That's like your principal value. I'm going to write that down. Principal. I think it's P-A-L. That's your principal value. And then 3% per year is what it's increasing by. Okay, so when it says increasing by 3%, that means on top of 100%, I'm getting an additional 3%, which is total of 103%, which as a decimal is 1.03. So that's why it's 1.03 in the formula, okay? And then X is the number of years that have elapsed since I've started to put that money in, okay? We're going to figure out how much money your investment will be worth in 4 years, okay? It's always a good idea to pay attention to your units, because sometimes they'll put this in months, and then they will say, how much is it after 4 years? Then you would have to insert the number 48 because it would be 48 months rather than 4 years. So be careful of that. So we put in 5,000, 1.03 to the 4th power, and practice typing that into your calculator so you can get that. I am going to plug it in real quick here, and I got 5627.54. So that's 5,670 or 27.54. So a 3% per year interest rate is going to gain me an additional $624 in those 4 years. That's not too bad, considering I'm not actually working for that money. So over 4 years, I'm making $627 by it just sitting there, okay? So then it says, when will your investment be worth $8,000? Okay, so I started plugging and playing some of these numbers, and I said, okay, let's say we plug in 5, which is just one more than this, right? If we plug in 5, I got 5796.37, which isn't a whole lot larger increase. We're trying to see when we get up to the $8,000 mark. So then I went a little bit bigger, and I said, okay, let's plug in 10. I said, let's go really big. 10 was 6719.58. Okay, so still not quite there. I said, okay, let's keep going. Let's go to 15. 15, when I plugged 15 in, I got 7789.84. Okay, so we're getting closer. We're in the 7, like we're almost to 8,000. So I said, I'm not going to go to 20. I'm going to go to 16. And 16 is at 8023.53. Okay, so here is your 15. Here is your 16. We have just gone over the $8,000 mark. So when will your investment be worth $8,000? It would be somewhere in the 15th year is where it will be. Somewhere in the 15th year. And then, you know, at the end of that 15th year, beginning of the 16th year, we will have definitely crossed over the $8,000 mark. So somewhere in the 15th year, between year 15 and 16. Okay. All right. Again, we're just plugging numbers in. Example 5, this is the last one, says, based on data from the last 15 years, the world population in billions, circle that. Anytime they say units, circle those so that you can pay attention to what that is, can be approximated by this function. Okay. So 2.5 is our original number. This is like our principal number. Okay. But our principal number is based on, number is based on billions, right? So our principal or our starting number is 2.5 billion. And our starting number, it tells me right here, is in 1950. So they're saying in 1950, or the principal amount was 2.5 billion in 1950, okay? And then it's gone up about this number right here would be an increase of about 1.85% per year, okay, to reflect that number, all right? So our starting number is 2.5 billion, and it's going up 1.85% per year, okay? Estimate the world population in 2015, okay? Now, we don't want to just plug 2015 in for X, okay? Because 0 corresponds to 1950. So if 0 is 1950, then 2015 would be the number like 65, okay? So we're going to plug 65 in for this X. And I think I went ahead and do that. You can practice plugging this in to see. I got 8.23. Let's just round it off at 2 decimal places. But that's 8.23 billion, okay? Which is probably about right. I don't know. Like, I don't think we were maybe quite to 8.23. I don't know. Maybe we're not to 8.23 billion yet. I think we're somewhere close to 8 billion maybe. I don't know. World population. World population. We are at 7.9 billion people right now, and it's 2021. So yeah, as of November 2021, it said 7.9 billion people. So this is a little bit of an overestimation. But again, you know, you're going to get that with formulas that you get, okay? In what year will the population be double what it is in 2015? So this is where we're going to have to plug and play, all right? The population in 2015 was 8.23 billion. So we want to figure out when that number is double. Okay, so when we double that number, it will be 16.46. And we're just going to have to plug and plug and plug and plug and plug. Okay, and I have not done this yet. So if you get a number, try plugging this in. I'm going to start with, let's see, 65. It was 8.23 billion. So let's go to, I'm gonna like double that number. Let's go to 130. If I plug 130 in for x here, this would be like 2.5 times 1.0185 to the 130 power. I'm just gonna change that, and I'm gonna see what it ends up being. It's probably gonna be way off. Okay, so this one is 27.09. So we way overshot this. Okay, so I'm gonna go back and let's try 100. So I'm going to go with 100 next. Okay, 100 ends up being, oh, we're close, 15.63. Okay, let's go like 105. Let's see. I'm just going to like kind of feel around. Okay, 105. All right, I'm going to go down here. 105 is 17.13. Okay, so we're getting close. Let's go to 103. We'll go right in the middle, kind of. Okay, 103 is 16.52 billion. So let's go 102 next, and we'll see. We're getting close. 102 is, yep, 16.22. Okay, so 16.46 is between these two numbers. So it's somewhere between year 102 and 103. So between year 102 and 103, which actually means if year 0 is 1950, year 102 would be 2052 and 2053. So somewhere between 2052 and 2053, maybe like July of that year, is when we would break the 16.46 billion number according to this model. Okay, so for now we're just doing the plug and play thing. Later on in this chapter we will learn how to actually solve and find the exact number without having to plug and do all that stuff in, but we will learn that later on. We'll finish the rest of this on Monday. You should be able to get a decent start on your homework assignment though, so do that now. Thank you.